So what I'm going to talk about in this lecture is really all of physics, actually, all of the known physics at the moment, plus a lot that's guessed. And so the lecture is going to be even more extensive than the ones before, because there I was only dealing with 2 particles, and now I have to deal with, I guess it's 24 particles. But first, I'm going to divide this talk into 2 parts. First, I'm going to talk about questions that are directly related to quantum molecular dynamics of itself. Supposing that was all there was in a system, electrons and photons, what problems are associated with that theory alone? And the second set of questions has to do with what is the relation of this stuff to the rest of physics, to nuclear physics, gravitation, and so on. So start with problems of quantum molecular dynamics, which I suppose now that the theory is completely understood and you know what I'm talking about because you were here at the other 3 lectures. Most shocking characteristic is this crazy framework of amplitudes, and if you would think about there being problems, you're sure that problems must be associated with that. But the physicists have been fiddling around with this now for 50 years, and we've gotten very used to it. A. B. All the new particles, all the new phenomena having to do with nuclei and higher energies, etc., always turn out to fit perfectly with everything that you can deduce from supposing it's a framework of amplitudes whose square is probabilities and interferences and so on all appear. So that the model structure of the world, the framework of the world which I described, has no experimental doubt about it. You can have all the philosophical worries you want, but there we are. Because it's an experimental science, we have no other way to go. There's another set of problems, which are technical problems, having to do with improving the method of calculating the sum of all the amplitudes. You make all these pictures, and you have to add all these numbers, and you have different kinds of techniques that are available in different circumstances, and of course that is what the graduate student learns how to handle and what takes so long to learn. And of course, since it's so technical, I'm not going to discuss it. That's just a continuously improving techniques for analyzing what quantum molecular dynamics really says in different circumstances. But we have one additional problem that's characteristic of the theory itself, we have a particular problem, a characteristic of the theory itself, which as a matter of fact was the reason why it took 20 years from the time it was first invented in 1929 till the time it was first satisfactorily used in 1949. And that has to do with this problem. We have in our theory, for example, if we start with an electron here, we have a certain amplitude that it gets to here, which we can supposedly calculate first by supposing it goes directly, and that amplitude is a direct function, a very precise function that comes from relativity that contains a particular number in it, which I wrote last time as ME. And I'd like to write this time as M sub in. Now that we put in to the theory. We have to just put it in and then find out what results we get and find out what number we have to put in there to agree with it. This is the amplitude that a particle starting at 1 will get to 2. I think I wrote it this way last time. And depends on the mass of the object. However, the real amplitude to go a long time from position 1 to 2, I also told you last time that the amplitude was constant in space, and you added this all together, then you'd find that the amplitude to find it at a time 2 simply rotated at a certain angular rate, the angle would keep turning, at a rate depending on the mass, m. But in fact, there is the total amplitude to get from point 1 to point 2 also contains other possibilities, of which this is one, that the electron could have emitted a photon and reabsorbed it, and the electron could have emitted 2 photons, or a photon twice and reabsorbed it, and a whole lot of other diagrams that you keep on going. Contribution from these various diagrams, if this one, for example, is of order c squared, where c is a number that goes every time there's a junction, or called a coupling, and c squared was equal to 1 over 137.03599 and so on. We haven't done it experimentally. We're not sure of this within a 3, plus or minus 6. And that's determined also experimentally so that the predictions of the theory agree with experiment. Now, the thing I'd like to emphasize is that because of the other amplitude, the real total amplitude to arrive at the time 2, supposing, let's say, that initially it was equal amplitude to be everywhere in space, does not revolve, the phase does not turn at exactly the original value, but turns at a different value because of the contributions of these other values. This one would go around at this rate, the angle, the amplitude to arrive is a complex number, which with time t2 changing, goes around. After you've added these, it's again a complex number, but it goes around faster or slower, different rates. Now what we measure when we measure the mass of an electron in an experimental world is the rate that it goes around. The mass of an electron is its energy. The mass and energy are equivalent, as Einstein showed, and energy is equivalent to frequency, as I guess it was de Broglie showed. And so I keep saying mass and energy and frequency interchangeably because I'm so used to that. At any rate, the frequency or the mass or the energy of the electron, the one that we're going to measure experimentally is not the one we put into the theory. So we have another mass, which is the mass experimental, which we could see would be expected to come out something like this. If the c-square was small, very small, and you want to forget it to 1%, forget that 1%. This term is of order c4. You would say first approximation comes from this amplitude, you'd get something like that. And then you'd have a correction because of this thing, which would have a c-square times it. In other words, some correction with 101%, something like that. A correction that you'd compute by adding these diagrams together, and then maybe c4 times another correction from this and so on and so on. That's easy to understand. Now, when we make calculations of any other physical result, it's much more convenient to express the answer in terms of this m, which is a measured value, than it is in terms of that. So we have a habit of writing all the answers. Always imagine we might start with a number like this, calculate everything, and express everything in terms of the experimental mass that we measured, which is the sum of all these things. So all answers are calculated in terms of the experimental mass. Now, if you've understood me at all, you probably don't understand why we made such a big fuss of that, because that's just a matter of convenience. It's just a question of whether I put it in here and compute that, put it in here, or whether I put it in directly. The difficulty is, and the peculiarity, the thing that bothers us, is that this correction that you multiply c-square by is infinity. And the fact that it comes out infinity because this function and the one for this was the electron one, and for the amplitude that the photon gets from here is the same from here to here, this point to this point actually, not 2 to 1. I shouldn't have said that. In here we're just going from here to here. That multiplied by the same function for zero mass and then added everywhere comes out infinity. And that caused a lot of trouble for the first people who invented this theory. They saw they were getting infinity for every answer. Because at every problem that they did, there was something like this in it somewhere. An electron going from one place to the other would always be possible to emit a photon and absorb it. Every answer to every problem was infinity. It was noticed by 1949. It was 20 years later, it was noticed by Beta and Weisskopf that if the answers were put in terms of M experimental, it looked as if, in spite of this being infinity, when you wrote the answers in terms of that and computed them, there was no infinity. All the infinities canceled out. So that if you had expressed the answer in terms of the final M and not in terms of this one, then everything would be finite. It looked that way, and it was just a matter of checking out that, in fact, that was true. That's what was done by Schwinger and Tomonaga and myself. They got prizes for that. But one way you could say all this is that this number is unavailable experimentally. It doesn't mean anything. You put it into a theory. Let's, for a moment, imagine it, so that whatever this is, I can always adjust this number so this comes out finite. If this is infinity, I put minus infinity in for that. And that's one way of saying what we ultimately are doing. Although this looks like it comes out infinity, we put minus in, this comes out, let's say, not infinity, 10 billion, right? Then we put in 9,999,000,999, only get 1. So if this, or whatever this is. So the idea is that this goes toward infinity in a calculation. We just say, well, just keep on adjusting the m so that it's to fix it back so that the m comes out finite. Now you laugh at that. because you have some kind of a feeling that's a dippy way to do mathematics, and it is. And this dippy way to do mathematics is the way we do this theory, because we don't never been able to straighten it out. But we do know that if we do this dippy way, we get results which agree with experiments. If it had been that this correction were finite, there would be no problem, of course, because the fact that this would be some number and there would be another number. But the fact that the correction is infinite is very annoying. And as a result of that, it has turned out it is not possible to prove at the present time that the entire theory of the quantum electrodynamics that we've written down is really self-consistent, that there's not some, if we calculate everything extremely accurately, we wouldn't get into some difficulty in itself, that the mathematical structure of the theory is self-consistent. There's a nervous condition that there's something wrong with the need that we start with a nice number and have to put minus infinity and play games like this. That annoys us, okay? So that there's one problem, what I have to say, is that in this, although this calculational scheme is quite definite and we know exactly what to do, this process, which is called renormalization, we are not satisfied that it's a mathematically legitimate process. But you notice that when we compute the 10 decimal places, it agrees with experiments. So it may be all right and may be a real theory. Another way to describe this business is the following. In making all these calculations and adding over all possible places for the, in this case, there's a contribution. 1 and 2 is here, but in our problem, where I'm having trouble, let's call this 3 and 4. Then we would have this at 4 and this at 3, multiplied by the photon going from 4 to 3, which is the same thing at 0 now. And when it turns out that when 4 and 3 are very close together, that these both things rise together as they get close together, but so much that when you add all the possibilities, you get infinity. So one way of saying this is, your whole idea that you can have 2 points infinitely close together is nonsense. Your whole thought that space can keep on going down to the last notch and you can use geometry to the very last infinitesimal distance is wrong. Suppose we stop these sums when 3 and 4 are closer to some very tiny distance. Let's say a distance that's shorter than any distance or any wavelength or anything we're able to get experimentally. Then this correction comes out quite small. Well, it depends. If you make the distance sufficiently small, then the correction gradually builds up. In order to make this correction term equal to this, so that this has to be 0, sort of. It turns out that the distances that you have to use are absolutely, well, I can't even, it's no use trying to describe them. They're like 10 to the 100 power or something like that, 10 to the minus 100 centimeters, whereas all we can do experimentally is 10 to the minus 15. That means some, I don't know, 80, 90 decimal places further on than where we are. So it's always possible that nature's different 5 or 10 decimal places down. 20 decimal places down. You don't like it 30 decimal places down? It's all right. The trouble is that we cannot make a model of that, a real model. If we stop these things at some distance, then the theory that we write is mathematically inconsistent. It gives probabilities that don't add up to 100%, or it gives negative energies, or it gives something silly. Of course, it gives these things with infinitesimal amounts, but it's not a self-consistent theory, and therefore we don't know. We do have this difficulty with this theory. We don't know whether if we stop the theory temporarily, it makes sense, or if we just go taking what we call the limit here, where we use everything and do the renormalization process, calculate everything in terms of the experimental mass, and then forget about the infinity, whether that's a mathematically sound thing. So I have to explain that in order to tell you the exact position of physics today. That's the problem. It turns out, in addition, there's the same kind of a problem about the sea. That also has a correction. If you were to have started out and imagine that 2 electrons were interacting via a photon, and they were an effective coupling C0, C0. And now you have a correction because the photon that goes along can make a pair, and then that could annihilate and make another photon. And that corrects this, and so on. And in exactly the same way, the effective coupling constant, which is measured experimentally. See, I cheated a little bit. I said it was that. It isn't. It comes out like this, that the experimental coupling constant is equal to C0 square plus corrections of the order C4. See, because you have 2 C's here and 4 C's here times a correction. Yes, you guessed it. That's right. This correction is also infinite and causes us the same nerve-wracking business. But this is measured experimentally. Make that 0, and it will come out okay, because 0 times infinity is finite. Never mind all that. If we put the results in terms of the experimental constant, then there's no difficulty, and all the infinities disappear. So in other words, we have to use the renormalization trick twice, once for the masses and once for the charges. Once for the coupling constant, which is called electric charge, and the other for the mass of the electron. Okay? And when we're finished, we get a coupling constant, which we have to look to experiment to measure. So that is simply a technical difficulty, perhaps, and maybe a real difficulty. But anyway, that's the slightly discomforting condition in which the theory is. That's the first main problem. Now, with regard to questions about electrodynamics, if you say, I accept that, that probably is okay, or if it isn't okay, I'll wait for some mathematician to find out for me. We then have the following interesting physical problems I mentioned before. Where does this number come from? From experiment. I know, but a good theory would have that this thing is equal to 1 over 2 times pi times the cube root of 3 times 6 and so on, so that you know what it was, if you know what I mean. It's a number that has to be put in, that nature has, or so to speak, if you're religious, you would say God has created that number. But we would like to try to figure out, if we can, a little clue as to how he thinks to make a number like this. For example, maybe why isn't that a 4 there, you see? Okay. In the same way, by the way, you might ask, in the same way, what is the mass? That is also a number. Yes, that's also a number. If you write the mass of the electron, and I'm always going to put the experimental masses down, it comes out a number. There's so and so many grams. And why is it that many grams? You first have to tell me why a gram is as big as it is. It's because somebody chose a gram, I think during the French Revolution or something. They decided such and such is a gram, and then the electron is so many grams. That's therefore not a real problem. But nevertheless, I'll put it down here as a problem. I'm not going to use grams because there's too many zeros. We have a particular unit which doesn't make any difference what it is, but we'll call it the million electron volts. It's the energy, masses and energy equivalent, that you get when you have a million volts and have one electron fall through that much difference in volts. And this mass is known many more decimal places, but I'm not going to bother you anymore with these long strings of numbers. So the mass of the electron is this, and of course we don't know why it's that particular number. That depends on why we chose the gram, the size of the electron, the volt, the size it is. Okay? And so that is not by itself a serious problem. But the reason I write it down is that it's going to turn out that there's a large number of particles in physics, not just electrons. There's, as I mentioned, several dozen. And they all have masses, and they're all different. And they're all the same problem. Where did this one get its mass? They're all relative to it. You can't play games with the grams anymore. One's a ratio. For example, you find one is 67 times this one. Why? So the masses are, in general, a problem, to which we do not know the answer. So we have no way to determine this mass. Now, that summarizes all of the problems associated with quantum electrodynamics. The most beautiful one is the coupling constant 137 point and so on, and all good theoretical physicists put that up on their wall and worry about it. There is, at the present time, no idea of any utility for guessing at that number. There have been from time to time suggestions, but they didn't turn out to be useful. They would predict that the number was exactly 137 when it looked, well, the first idea was by Eddington, and experiments were very crude in those days. The number looked very close to 136. So he proved by pure logic that it had to be 136. Then it turned out that the experiment showed that that was a little wrong. It was near 137. So he found a slight error in the logic and proved with the pure logic it had to be exactly the integer 137. It's not the integer. It's 137.036 6-0. Every once in a while, someone comes out and they find out that if they combine pi's and e's and 2's and 5's with the right powers and square roots, you can make that number. It seems to be a fact that's not fully appreciated by people who play with arithmetic, that you'd be surprised how many numbers you can make by playing with pi's and 2's and 5's and so on. And if you haven't got anything to guide you except the answer, you can always make it come out even to several decimal places by suitable jiggling about. It's surprising how close you can make an arbitrary number by playing around with nice numbers like pi. I mean, and therefore, throughout the history of physics, there's paper after paper of people who have noticed that certain specific combinations give answers which are very close in several decimal places to experiment, except that the next decimal place of experiment disagrees with it. So it doesn't mean anything. Okay? Those are the problems of quantum electrodynamics. Now the next part is the connection of quantum electrodynamics to physics, to the rest of physics. And we're going to have a good time now for the rest of the lecture because I'm going to tell you all about the rest of physics. And you can compare the laws of the rest of physics with the laws of quantum electrodynamics. But first I must say immediately that the rest of the laws of physics are not known as well as quantum electrodynamics, and therefore what I have to say is to a varying degrees uncertain, nowhere near as certain as the electrodynamics. So first there must be a connection because we have to discuss one point. The photon, which couples to the electron, also couples to the nucleus. That's why the electron is attracted to the nucleus. So there's something inside the nucleus that couples with a photon. And we sometimes say it's charged. To say a particle is charged or something is electrically charged is merely a statement that it couples to a photon. A photon is absorbed by it or emitted by it. That's what it means. Anyway, nuclear particles are charged.